Hello, my name is Stavros, and today we are going to test a small device that is capable of checking DIL 14 devices containing logic gates like AND, OR, XOR, etc. etc. Now, here we can see the schematic of the design, which contains quite a few unnecessary stuff, although we need to explain what each of them are. Right here we see the power supply for the circuit board, which doesn't actually affect the simulation, but it's there for the PCB design. On the bottom we see the Bluetooth terminal. It's separate from our PCB, but it has to be connected through the J3 connector, meaning that this little connector is going to be included in the PCB design but does not affect the simulation. This is the 14-pin socket where the IC is going to be inserted in. Pin 7 is the ground, and while pin 14 is the power supply, we can see here. The reason we are seeing two relays is because the design relay actually has a package, so we can include it in the PCB layout right here. That's it. While it cannot simulate, it doesn't have a file inside. But the sim relay is the opposite, so we can use both of them at the same time while excluding them from the process they cannot do. Therefore, you can actually consider them one relay. After that, we see many logic gates here. These are only used for the simulation because we don't have actually an IC to put inside the socket. Therefore, the circuit is excluded, and we manually connect these logic gates. As you can see, U3 is connected to RD0, RD1, and RD2. And now to jump into the simulation, first we have to build it. Build successfully. It gives a fair amount of warnings, but that's for the text, so it doesn't actually affect it. So, what happens now? When we start the program, it goes through the initialization process, and that involves setting up various variables, etc., etc., and then it outputs the message, this message, the menu, so the user can see it on his phone, and the whole message is transmitted through the Bluetooth device here. So now it only includes these 6 ICs on the list, and the user is then prompted to enter a number from their phone or whatever they have, see, and depending on the selection of the number, they determine which IC is under test. For example, now let's press a number that it's not on the list. Let's press 9. It shows a message of invalid selection, and then the process is repeated again because that number does not correspond to any IC within the database. Now let's press, now we have the XOR gates, we should press number 5, but let's say we press number 1 for AND gates. It outputs the message error, the IC is malfunctioning, or selection IC mismatch, which makes sense. The moment we make a selection, the program generates the expected results and the I/O configuration, of course. Based on the expected results, then it measures through the gate's outputs. This would be RD2, RD5, and whatever it is here. And if the arrayed outputs match the expected ones, it means that the IC is functioning properly. But because AND gates and AND gates obviously, XOR gates, obviously have different truth tables, it outputs the error message. Now, if we select the correct one, XOR gates, the outputs that the program is reading actually match the expected ones from the truth table of the XOR gates. Therefore, it outputs that the IC is functioning properly. Now, let's simulate a false condition. For example, let's delete RD5, which means that this is an open circuit. Let's run the simulation again. Select 5 for XOR gates, like we have here. It outputs an error because it can never read logic 1 from this output. So the IC correctly the program correctly determines that the IC is not functioning properly. Now let's test the AND gate scenario. We replaced all the XOR gates with AND gates, matched them correctly, and now we have to run the simulation. We press run, we select number 1 for input AND gates, and the IC is functioning properly. The process restarts again naturally, and as we can see, after the process finishes, the power from the IC is cut off and therefore can be removed safely. Also, all the inputs from the circuit and outputs are turned to logic low, therefore they as well don't have voltage. Now, let's remove one connector. Let's remove this one, for example, and let's run again. We run for AND gates. The IC is malfunctioning correctly. Now we have selected the OR gates to be tested. Everything is connected properly, so the program should indicate that it's behaving correctly. Now let's press 2 for OR gates, as it says here, and it's functioning properly. The process restarts. And now let's cut a wire. Let's cut this one. Select again, number 2, and the IC is correctly malfunctioning again. Now let's check the NAND gates if they're working properly. So NAND is number 3, correctly selected, IC is functioning properly. Now let's stop again. Let's cut this wire, for example, or this one as well, but it doesn't really matter. If you cut one, it will still do the same. NAND gates, the IC is malfunctioning, or possible mismatch, which wasn't the case, of course. And now let's test the NOR gate scenario. NOR gate should be number 4. The IC is functioning properly as stated. The green LED is lit on. Let's now cut a wire. We cut this wire. We simulate again. Number 4 for NOR gates. And as expected, it's malfunctioning. Now let's check the NOT gate scenario, which has a different I/O configuration, because previously we had 2 inputs and 1 output. Now it's 1 input and 1 output, and it has in total 6 gates. But the only difference is inside the program, really. Now let's check NOT gates, and since everything is connected properly, it indicates that it's functioning properly as well. Now, if any of the gates has any sort of damage, let's simulate again, press 6, and the IC is malfunctioning. It outputs a message that it's malfunctioning as a whole. It doesn't yet have the ability to specify which gate exactly is malfunctioning. Now, it was suggested that we try to extend the design to support DIL 16 family products, and that was actually a very simple process. We replaced the socket with a 16-pin socket, but that comes with an inherent difference. Before, pin 7 would be connected to the ground, like it's shown here when we are testing DIL 14 devices, but when we're checking DIL 16 devices, pin 7 actually has to be connected to an input in the controller, and pin 8 has to be connected to the ground. If the hardware is supposed to support both of those designs, we had to add 2 small jumpers. Alternatively, somebody can use a switch. When we are testing DIL 14 devices, the jumper connects pin 7 to the ground as it should be, and JP2 should be open, therefore isolating pin 7 from the input of the controller. When we want to test DIL 16 devices, this jumper JP1 should be open, therefore pin 7 would be isolated from the ground, while this pin JP2 should be closed, and therefore pin 7 will be connected to the controller's input. We actually did some slight movement here. This is the first jumper, while this is the second. We had to move the transistor Q1 to this position. It could be located elsewhere, but this was the best. And without increasing the size of the PCB, we achieved to incorporate support for DIL 16 devices. Also, it came with some changes in the code, because these have to be included. However, we did change the code, but we didn't include any products for that category. Now let's start the simulation. We have XOR gates everywhere. The initial menu has changed. Now the user is prompted to select at first which family he wants to choose from. Here we have DIL 14 and DIL 16, and we have to press either 1 or 2. Let's press 5, for example. We have to choose again because it's not working properly. There is nothing attached to that number. If we press DIL 16, the routines that perform the same checks as before had to be carried out. However, since we haven't actually made them, the program outputs only this message that this category is not yet supported, and basically the user has to choose again. If this program is developed, then within that code, that part of the code, there should be the routines that perform similar checks like before, and therefore testing the device. Now let's check DIL 14. When we press DIL 14, the previous menu like before appears, and we can choose whatever is on the list. Let's press a random number, number 8. Again, invalid selection, we have to choose again. If we choose, let's say, number 1 for AND gates, we currently have XOR, the IC is malfunctioning, process finished, the IC power is turned off, and now we can remove. Every time the processor restarts, we have to choose from the menu again. Let's say again DIL 14. Now if we select the correct number 5 for XOR gates, the IC is functioning properly and the processor starts. And one last check. Let's disconnect a random wire, run again, DIL 14 family. Okay, there it is. Number 5 for XOR gates, and the IC is malfunctioning. So basically this code fully supports both DIL 14 and DIL 16 if it's ever built, and it can test DIL 14 with a different circuit than before.